So in the video that you watched on AP Classroom, you saw the definition of a limit. What is a limit? Is a value you can get arbitrarily close to. And we would read this, the limit as x approaches 5 of 3x minus 8 is equal to 7. And sometimes we can find limits by just, like for this one, I just plugged in 5. Technically, that might not be the answer. Plugging in 5 might not be the answer. We saw that in some of our examples yesterday, or I guess it was like 5 days ago now already, since we've done some limit stuff. But in this case, 3x minus 8, right? If here's minus 8, that would be my y-intercept. And I would have a slope of 3, straight line here. And the idea is, when I get close to 5, from the left and from the right, because my original graph is a straight line and includes everything, does it make sense that it's going to be exactly my y value at 7 there? So if we have graphs that are continuous, and that's going to be a definition we're going to flush out, that you can draw without taking breaks, without any jump discontinuities, the limits often are easy that you can just plug things in. So we're going to try to evaluate a bunch of limits. And we're going to learn some techniques to do that. So there's some limit theorems. If inside your limit, you just have a number, okay? Your answer is always 8. Well, what would it be if you got close to x equals 3? It's still 8. If we graph this, if you graph the 8, do you see that 8 is just a horizontal line at 8? And it's 8 for everything. Doesn't matter what x is. So this question is saying, well, if it's always 8, and you got really, really close to 3, what would it be? It would still be, oh my goodness, really, really close to 8, because it's always 8. They thought this was important enough to call it a theorem. Some things that are theorems are really so obvious that they're complicated. Like this seems too easy to be anything. That is what it is. The limit as x approaches a of x is a. So again, what I'm going to do is I'm going to translate this to numbers to help, because in variables, it can look confusing. Once you break it down to numbers, it's like, okay, that makes sense. Now c could be any number, a could be any number. Here x is a variable, so I'm doing the limit as x goes to 2 of x. Well, the inside is my graph. If I graph y equals x, do you see that that is the perfect diagonal line like this? And if I got close to, say, 2, from this side and from this side, well, on my graph, I have 2 comma 2. Does it make sense that my y value would also be 2? So what a limit is really looking at from a graphical perspective is as x gets close to something, what does the function or the graph, what does its y value get close to? So the inside here, we can think of as the graph y equals x. And as x gets close to 2, what would your y value be in that situation? It would also be 2. Can you see that that's true for any number? If you got close to 3, it would be 3. If you got close to 4, it would be 4. If the limit as x goes to c of f of x, the limit as x goes to c of g of x, a and c are real numbers, then the limit as x goes to c of two functions added separately is the same as finding the limits of each one on their own. So that means if you would know, this is, for example, we could do the ones that we already know. Right, those are two that we already know. This one's going to be 2. This one's always 9. This one's going to be 9. You could now do this. Oh, I want to make, sorry, one little typo here. I want to make that number the same. What is the limit as x gets close to 2 of x plus 9? This is not really hard. It's going to be 11. Because the limit as x gets close to 2 of just x, you know that that's already 2. And the limit as x gets close to 2 of 9, well, that 9 is always 9. Limits you're allowed to break up. You're going to not ever write that out. You probably just do this one in your head and get 11. But you can break them up, and sometimes that's really helpful. So if you're adding, you can break up the limits. If you're subtracting, you can break up the limits. If you're multiplying, you can break up the limits. And if you're dividing, you can break up the limits as long as you don't divide by 0, because dividing by 0, even in calculus, is still bad. And if you have a number out in front of a function, you can just bring that number outside. So something we can do with this last one, using what we know already. Limit as x goes to 7 of 5x. According to our limit rules, I could bring that 5 out in front. And say the limit of x goes to 7. Well, you know from theorem number 1, this is 7, right? So the limit as x goes to 7 of 5x will be 35. And one of the strategies that we're going to find out today is if you can plug in a number, often that's going to be the limit. Can you see that you could plug in 7 into 5x and get 35? And you would have got the same as breaking it up with your limit theorems so far. All of these are pretty straightforward, but sometimes in math, you're not allowed to do things like this, right? Logs are a good example. If I'm multiplying inside a log, can I just multiply the 2 logs separately? No, you can add them. Oh, that's a weird log, right? So we have to be careful. Sometimes things seem obvious with theorems, but as you get into more complicated math, you have to break things down. Are we allowed to do this with limits? The answer is yes. So limits so far are nice because you can break them up and do them separately. Theorems 8 and 9. So if m and n are integers, which makes this a radical, and as long as n doesn't divide by 0, because your n can't be 0, because then you would divide by 0, then we can do limits like this. So again, I'll put some real numbers in here. Limit as x goes to 3 of x to the 5/3. According to our limit theorems, what I can do is I can do that. Put brackets there and just do limit as x goes to 3 of x. Well, that's going to be 3, and then I would have the 5/3 left. which means if you can find the limit of the inside, then the exponent part can just get added on at the end. And that the dividing by exponent part, you know that dividing by 2 would be the same as a square root. Dividing by 3 is the same as a cube root. So we could write this in radical form. If you have a radical and a function inside, you could just take the limit of the function inside and then do the radical after. If p is a polynomial function, this one's really powerful. Means you can just plug in the value. And the reason for that is, just like the straight line, y equals x, you can draw it all in one thing without lifting your pen. Any polynomial, x cubes, x to the 4s, they're continuous and you can draw them all the way along. So every single limit on a polynomial, you can just plug in the value to figure it out. Same thing with rational functions, as long as you're not dividing by 0. If you can plug it in, you get the value. If you can't plug it in because you're dividing by 0, then there's another problem. So this gets to this important idea. What is a continuous function? And this is so important for calculus. This is not the official mathematical definition. A continuous function, if it can be drawn without lifting your pencil. Can you draw a parabola, the whole thing? Yes, without lifting your pencil. That makes it continuous. Almost every graph you've done so far has been continuous. There are some that have discontinuities. This one, you cannot graph without lifting your pen because one part is here and it is not joined to this part. You can't draw both parts without, right? Your calculator, you have the TI-83. The TI-83 really struggles with it. It does this. The old calculator, you ask it to draw, it goes like, ah. It's like it connects dots and it adds an extra line there. But that line doesn't actually exist because there's an asymptote there. The TI-84s fix that problem. They don't draw that extra line in anymore. Okay? So we would say this parabola is always continuous. We would say the 1 over x graph is continuous from here to here, then has a point of discontinuity, and then is continuous or has an actual asymptote, but it has a place where it's discontinuous, and then it's continuous on the next point. If the graph is continuous, the limit is super easy to figure out. If you ever would like to know official definitions, I do have a math dictionary. Look how big this is. The only thing in this is math terms and it has the definition of everything. So like, oh, it's got the factor theorem. It's got the, like stuff that you've done. What are things that, what are fun definitions in here that you've done already? Even has some easy divisor. A number or polynomial that divides another number or polynomial. Something you can divide by. So, if you ever need to know a mathematical definition, you could look up in here. Continuous, it would do it officially. We'll look at it more official later on. But right now, we're just getting the general concept. If you can draw it without lifting your pencil, your graph is continuous. Which leads us to the plug-in method for figuring out limits. This makes life really easy. So easy that they almost never ask you these questions because it's like so obvious that it's super easy. If you have a continuous function which you can draw without lifting your pencil. You could just plug in whatever the number is to get your limit. You don't have to check 1.9, 1.99, 1.999, and 2.01, 2.0001, 2.000. You get closer and closer and closer. You can just plug in 2. If I plug in 2 into here, what do I get? 3. That's the answer. And limits are super easy in this situation. This is a rational function. Theorem number 9 said, if you have a rational function and you're not at the non-permissible value, right? Am I allowed to plug in 16? Would that make me divide by 0? No. So here we get some fun math. I'm pretty sure you can do the top. Square root of 16 minus 1? Top's going to be 3. What is 16 to the 3/4? You can do this. 16 to the 3/4. Okay? You have options here. 16 to 3/4. You could either do this. Right? Everybody knows 16 cubed in their head, I'm sure. And then whatever big number that is, do the 4th root. Or you could do this first and then cube it. I think that might be a little bit smaller numbers to work with. What's the 4th root of 16? 2. What's 2 cubed? 8. And so our answer here is 3/13. Something, I don't know, you might like this. 16 to the 3/4. Well, 16 is 2 times 2 times 2 times 2. Take 3/4 of that. You got 8. That's kind of cool. And does that always work? Yeah. Right. 32. 32 to the 2/5. 32 is 2 times 2 times 2 times 2. 2/5 of that will be 4. Pretty cool. Because if you take the 5th root, you get a 2. And then if you square it through deep multiplication 2 times. But I like playing around with numbers, so when I find something fun when I played around with it, I'll try to show it to you. But then we get limits that aren't super easy. We call those limits like indeterminate forms or 0/0 limits, because this is going to be crazy. Sometimes 0/0 will be infinity. Sometimes 0/0 will be negative infinity. Sometimes 0/0 will be 7. And sometimes 0/0 will be impossible. And you'll have to figure that out. So those we call indeterminate forms. And a function is discontinuous at a point if you cannot draw the graph without lifting your pencil. So we had this in grade 12 when graphs had holes in them. You actually have to stop at the hole, lift up your pencil, go on the other side of the hole, and draw. And then you would circle that hole afterwards to show that there was a point missing there. So an asymptote or a hole shows where a function is discontinuous. So here, you try to plug in 3. What's the bottom equal to? 0. What's the top equal to? 0. Okay? This is the indeterminate form. Okay? Never, if they watch, this is like little tiny nuance thing. You never write equals 0/0. You can, in brackets, go 0, well, that's, oops, my zeros were way too close to each other. In brackets, you can go like this, maybe. 0/0 indeterminate form. AP exam is happy with that. But if you say it's equal to 0 over 0, they have issue with that. It's not equal. It's going to be equal to something. Do you remember graphing this in grade 12? What would you do? You would say there was a non-permissible value at 3, but the 3's cancel out, so that made it a whole. And then you would say, what am I left with? I'm just left with y equals x plus 3, and I would draw x plus 3 with the whole. Right? This is y equals x plus 3 with a hole in it, because 3 is still a non-permissible value. So we can actually say, I know what the limit is. As x gets close to 3, here's 3. As my x values get close to 3 on my graph, my y values get really, really close to 6. Do you see that the left side limit and the right side limit are the same? For a limit to exist, coming from the left side and coming from the right side, they both approach the whole. Even though the function doesn't technically exist at that point, the limit does. So graphically, we could say that the limit as x goes to 3, this is going to equal 6. But all of you are normal students and love graphing so much that you would rather take the more difficult way of just doing algebra. No, it's not more difficult. But if you had this, can you see that these would simplify? And if they simplified, now you could plug things in. Because x plus 3 is a continuous function, so then you could plug this in and find out your limit is 6 that way as well. So if you have the indeterminate form and you can simplify it, so you can plug things in, then you can find the limit that way. So what we're going to do is we're going to develop strategies to simplify so we can plug things in. Because initially, you weren't allowed to plug it into 3. Because you would get the indeterminate form, 0 on the top, 0 on the bottom. But if we simplify it, then we can get our answer. So as we said before, even though the graph is discontinuous at 3, 6, the limit still exists. Because coming from the left side and coming from the right side is exactly the same. You're going to like the algebra part. But it's nice to see the graph, how that works. So all your graphs from grade 12 that have holes, those would all have limits that exist at that hole. And the simplifying just helps you find it. Do you remember how to factor? Good news, you get to factor lots in AP Calculus as well. Sometimes I want to take, I've taken my either calculus or grade 12 students, and when we're just learning factoring in grade 10, I like, hey, do you want to just tell them if this is going to be important and you're going to use it later in math? It's like so important. So do you remember how to factor? Did you get the right answer for this one? Oh, it's a tricky one. This is one of the trickiest easy ones. Why? Because your brain probably went to 6 and 4 first. And if you don't check it, you might get it wrong. Did anybody think 6 and 4 first? Just seeing the 10 and the 20? No, you guys are so amazing. Okay, I'm sorry. You got to. Wow. This is where someone like, 6 times 4 is 24? There's a couple of them out there that exist where there's 2 numbers that seem to work, but only one works. You want to see the other one? All right. This one I like. Because what do you want to do? You want to do 2 and 3. But what is it? It's 6 and 1. Oh, yeah, you did the 2 and 3, right? So one thing when you factor, it doesn't take much mental math. After you factor, quickly multiply it out to see if you did it right. Can save you hours of time rather than later on finding, oh, I'm now 10 minutes into this question and realize I factored wrong in the first 30 seconds. Now I have to go back, change that, and then I still got 10 minutes to do with the new numbers. So it's worth checking as you go along. How about factoring when it's more difficult? Okay? So, if you remember, like there's lots of techniques and there's shortcut techniques out there. Those are all fine. If you remember them, you can use them. If you don't remember them, they're not very helpful. And then you either have to like find somewhere to refigure them out, or what I'm going to show you two things that I like to use for factoring that I hope you find useful. Okay? Now, factoring is the opposite of multiplying it out. And when you multiply it out, like you would have, right, all of these distribution arrows, right? Oh, for the French people, in English we like to say FOIL. Because you multiply the first ones, you multiply outside ones, you multiply inside ones, you multiply last ones. So you'll be like, oh, you just FOIL it, and you're in French immersion, you're like, what the heck are they talking about? They're saying you just distribute everything. Okay? But they have this word FOIL. And the word FOIL, and if you see what's happening, is really helpful for factoring because your first ones always give you that one, and your last ones always give you this one. Your outside and inside always will combine to be that. And knowing that factoring is the reversal of distribution can be a really good strategy for figuring it out. Now this one's complicated because I've got a 6. Why does the 6 make it complicated? Because you have options, right? It could be 6 and 1 or 3 and 2. That makes it a little bit complicated. Some people just say, I'm going to start with 6 and 1 and see if it works. If it doesn't work, I'll go to 3 and 2 and see if that works. Okay? I personally, then, because the 6 is complicated, I might start with my last one. 5 is not complicated. 5 is a prime number. The only two things that multiply to give you 5 that are nice whole numbers are 1 and 5. And if I start with that, 1 and 5, it really doesn't matter if I do 5 and 1 or 1 and 5 at this point because I have no order yet. Once I have that, I can look at my 6. And if I do 6 and 1, I'm going to have my outside 30, my inside 1. Absolutely, that will not work. If I put my 6 inside here and my 1 here, I'll have 5 and 6. Will that ever give me 7? No. I know very quickly that 6 and 1 will not work. I go to 2 and 3. Okay? If I do 2 here and 3 here, I'd have 15 and 2. That doesn't give me 7. But if I do 2 here and 3 here, I would have 10 and 3. That seems to get 7 if I would subtract. How would I subtract? Well, I need negative 7, so I would want minus 10 on my outside and plus 3 on my inside. And you're connecting factoring to multiplying it out, which is a really, I like that for factoring because it should make sense. And you can use this to factor. Okay? There might be some, though, that you're like, everything I've tried, when I tried the right one, I made a mental math mistake and it didn't work. And now everything I seem to have tried doesn't work. You can also use your quadratic formula to help you factor. So for example, if I would solve this with my quadratic formula, negative b plus or minus b squared. Quadratic formula isn't easier. Minus 4 times a times c over 2 times a. When I simplify this, I get 7 plus or minus. This will be plus 120, 169 over 12. And if in your quadratic formula, what's inside the square root is a beautiful perfect square, it means you could have factored it. Do you see square root of 169 is 13? So if I do the plus, 7 plus 13 gives me 20. 20 divided by 12 reduces nicely to 5 over 3. And if I do the minus, 7 minus 13 is negative 5. No. What did I do wrong there? Negative 6. There we go. Negative 6 over 12, which will give me negative 1/2. Can you see if you were solving a question and you got negative 1/2 that the factor might be 2x plus 1? And can you see if you got this, the factor might be 3x minus 5? How that matches up with our factoring. Okay? Factoring it directly probably is still faster in most places. So again, we want to get really good at factoring directly. But there's your answer. Does it matter the order that I write it? No, because multiplying is the same either way. Do you remember factoring out a common factor? So if something has a common factor, we would want to take it out. And then you would have to check, can you factor this further? I would try it. This one's actually really easy to try because the 3/8 only gives you one option. It would have to be that if it was possible. And the 1 only gives you one option. It would have to be that as possible. Look at your outside and inside. Does it ever make 7? Adding or subtracting? No. So mental math, I can pretty quickly determine it cannot be factored. Do you remember differences of squares? So if it's a difference of squares, which means this is a perfect square and this is a perfect square, then you get 3x plus 5 and 3x minus 5. And we have a name for when two things are identical except for the sign in between. We call those conjugates. Remembering that name can be helpful because some strategies that we're going to use in finding limits is like, one of the strategies is like, hey, you should multiply by the conjugate. And you're like, what's a conjugate? Then you're not going to remember the strategy. So, if we have those strategies for factoring, we can now evaluate the following limits. Can you see if you tried to plug in that first one of 0, you would get 0 over 0. So this is the indeterminate form, but do not write equals 0 over 0. Put in brackets, 0 over 0 is the indeterminate form, but never, don't do this. Don't do that. This is actually going to be equal to a number. How do we find that number? Well, let's see if you could factor and have things simplify. In both your numerator and your denominator, you have a common factor. We can take out an x squared. And then those x squareds would simplify. That's nice. And then what we're left with is something you can plug in 0. If I plug in 0 now, I get 8 over negative 16, which is negative 1/2. Which means if you graph this, this is sometimes fun. Go to Desmos, type that in. See what the graph looks like. It will have a hole at 0, negative 1/2. This is grade 12, you could graph this. Right? Degrees bigger on the bottom. Do you see that you would have a horizontal asymptote at y equals 0? Do we have non-permissible values on the bottom? Yes. At plus or minus the square root of 16 over 3, you would have vertical asymptotes. Then you would plug in points and see what it looks like in between, and you would have a hole at 0, negative 1/2. But again, you probably wouldn't want to graph this right now, right? You like just getting the answer is much nicer. This one, if you plug in 4, you get 0 on the top and 0 on the bottom. However, we can factor. And if we factor, one of our non-permissible values goes away. Meaning in the graph of this, you would have a hole. And after you've simplified it, now it's perfectly fine to plug in 4. This graph would have had a hole at 4,4/7. And so really, what is a limit on a graph with a hole? Well, if you're getting close to that hole, it's finding the y value as your x value gets close to the non-permissible value. All right, you want to try the next 4 factoring on your own? Ooh, we got some tricky ones. Try the next one. We'll do E and C together. D and E. Try F on your own. I put up the answer for C. Did your factoring work on the top? Okay. Which is easier to factor, the top or the bottom? I think the bottom. You take the 3 out as a common factor, it's difference of squares. Then, surprise, surprise, there is a way to cheat in limits. If you think that this limit should exist, then the x going to -5 would make the x plus 5 the problematic one. That would be the one you'd want to cancel. So if I was guessing and checking, I would just start by putting an x plus 5 on the top. And if I put the x plus 5 on the top, do you see that it would have to be 4x to get 4x squared? And it would have to be -3 to get -15. And then I would check it, because multiplying it out is a lot faster than actually factoring. And it works. And you cheat a little bit. I shouldn't teach you this. Does that make sense, though? As a way to like get the factoring quicker? Oh. That's what I think that was what I enjoyed doing in high school math. Figuring out ways I could cheat this. It's not good. It's either I had either a life of crime or a math teacher. I had to go into one of those two. So, fortunately, math teacher rather than life of crime, cheating the system. Okay, D. What can I do with D? Oh, I like D. D is fun. So one option. You could multiply it out. And then h minus 3 squared, you could FOIL or distribute that and get h squared minus 6h plus 9 minus 9. Then the 9's nicely go away. And you have a common factor of h, which you could factor out. And this is the goal in a limit. I want the bad value to go away. I want that to go away. If it does, now this is easy. Now I can plug it in. I'm just left with h minus 6, and if h goes closer to 0, then I just get -6. But what I like about D is you could do D as a difference of squares. Because you've got something squared minus 9, which is something else squared. This is not your typical thinking, but it's really cool if you do it that way. Look, if I factor the difference of squares, I would have h minus 3 plus 3 and h minus 3 minus 3. And in this one, the minus 3 and the plus 3 would just go away, and then my h's would go away, and I get h minus 6. I'll show a little bit more work than that, right? I get h minus 6 that way as well. That's kind of cool. Did you know you can factor differences of squares even if they're not differences of squares? By just like expanding your rules for factoring a little bit. That's x plus root 5, x minus root 5. Yes, I know for factoring we were stuck on whole numbers, but it doesn't mean you have to be. Makes sense, right? That one's pretty cool. You could use Pascal's triangle and your binomial theorem to expand 2 plus x completely. Then your 8's would nicely go away. And you could factor out your common factor of x. And your x's would nicely go away. And the box won't nicely go away. I don't know why. There we go, and you get 12. Very, very cool. This might be quicker if you could factor difference of cubes, which we'll learn. Because you probably don't know how to factor the sum of cubes or difference of cubes in your head yet. But we'll learn it. That would probably be quicker, but you could expand it completely. If you don't want to use Pascal's triangle, you could have just multiplied this out bit by bit. We'll leave F and the other ones for next time. Try F on your own.